Okay, so I am back. So we're going to go through our second example that I want you to be comfortable with before spring break, and that is sheets of charge. So if I have a sheet of charge, I'm going to do it like a side on. So if we're looking at it head on, this would be like, some big old sheet of charge. But if I just rotate this, so I'm looking at it from the side, let's say it's some kind of conducting material, some sort of metal, and it has, again, I'm going to make the charge positive, it doesn't really matter, make the charge positive. Okay, so this is not a wire, to be clear, even though it looks the same as my last picture, because if I spun it around and instead of it staying one long thin wire, it would be a full sheet of charge as I had drawn here. Okay, so it is different, but similar to what I had before, because these are positive charges coming off the sheet, I'm going to have electric field lines that come out from all directions. If this were instead negative, everything about this picture would look the same, except that these field lines would be pointing in and not out, right? So it looks pretty similar to what we just did, just like the cylinder problem. I'm essentially deriving this for you, and then once I do that, the math that I come up with is the equation you would use for any sheets charge or sheets problem. So the Gaussian surface we pick to deal with a sheet of charge is actually another cylinder, but this cylinder, instead of standing vertically, we actually spin it around so that you would have a large cylinder like this, where its face, the circular face, was as big as your sheet of charge. I should have done this in a different color. And I'm about to get a different marker to do this. It would look something like this. So the field lines, let me draw that in green just to see if it looks a little clearer. Okay, this is my Gaussian surface. Oh, look at that. This is the ugliest cylinder too. Okay. So the field lines would actually, in this case, be, whoa, because they're coming out from the sheet like to the left and right. Again, I would say your book does a much better job drawing this. If my picture makes no sense, go look at the book. But the field lines actually pierce the two faces of the cylinder and not that like rectangular body part. So you have this face, which is a circle, and this face, which is a circle. And we know that the area of a circle is pi r squared. But actually in this derivation, they just call the area of the circle A. So let's just call that A. And so if I were going to try, so again, if I want to find A, it's pi r squared. But if I were going to try and find the application of Gauss's law, I would say epsilon naught times my net flux is equal to charge enclosed. And epsilon naught times my net flux is E times A is equal to charge enclosed. But if we actually go and look at this E times A, right? If I call the face of the circular face of this cylinder A, it actually pierces two of these, right? One on either side of the sheet. So epsilon naught times 2EA is really equal to the charge enclosed. When we look at the specific, when I take what flux is and look at the specific geometry of this thing, because I have field lines piercing this side and field lines piercing this side. So that's where that 2 comes from. Okay, and so I could use that to find the, again, usually it's the electric field, like, because we otherwise wouldn't know how to. This is another continuous charge distribution. If I needed to find electric field, I'd either have to do some intense calculus or use what I'm doing right here. So typically we would say, okay, electric field is equal to charge enclosed divided by 2 epsilon naught times A. Now, there is another charge density used here often. So we saw this one for cylinders, and this gives us charge density per unit area. So it's like Q, or I'm sorry, per unit length. I'm jumping ahead of myself. Q over L, and it's used with the wires. So we like that with wires. When I say cylinders, I mean cylinders surrounding wires. And then we see this one here. This is a Greek letter rho. And this is often used for sheets of charge It's just the way things are measured. That's where these things come from. And this describes charge per unit area. So we would say rho, charge density, is equal to charge per unit area. And so I can rewrite that. Charge per unit area is equal to rho. So I could say electric field is equal to rho over 2 epsilon naught for a single sheet of charge. This, I'm just rewriting it over here where I have a little bit of room. This is the equation we often use when we are solving problems with sheets of charge. So if I give you a sheet of charge, typically you would be given the charge density for it, and then it's just plug and chug to find the electric area, or electric field is just plug and chug. Now, we can have slightly more complicated problems, and those would be when we have multiple sheets of charge. So I'm going to do one practice problem that involves 2 sheets of charge, because again, one, just plug and chug. If there are 2, you have to think just a little bit harder. So let me set that up. This is the one from the PowerPoint. Okay, so we have, let me grab the book so I draw it correctly. We have 2 sheets of charge. One on the left that is positive. Again, we're looking at it from the angle where we just see the ends. And the other on the right that is negative. Okay, something like that. And they are slightly different in their charge densities. So the charge density for the positive sheet of charge, which is again that rho value, is plus 6.8 microcoulomb per meter squared. And the charge density for the negative one is negative 4.3 microcoulombs per meter squared. So just a way of describing how the sheets are charged. And so it says find the electric field to the left of the sheets, between the sheets, and to the right of the sheets. So we want to find the electric field over here, in the middle, and to the right. So we say, okay, this is not something I can use KQ over R squared for. This is a continuous charge distribution. And so the electric field from a continuous charge distribution from sheets is equal to, we just said, rho over 2 epsilon naught. So that's what I just derived for you. And so it is good when you have multiple sheets to draw your electric field arrows, kind of like what we would have done in the previous chapter, so that we can figure which way these things are pointing. So for the sake of labeling, let me call this thing sheet 1 and this thing sheet 2. Okay, so on the left, the electric field from sheet 1 is to the left, because positives point out, so that's E1. And from sheet 2, it's to the right, E2. In the middle, the electric field from sheet 1 is to the left, so E1. And from sheet 2, it's also, I did say to the left, I mean to the right. It's also to the right. They're both in the same direction. And over here on the right side, the electric field from E1 is to the right, pushing away. And from E2, or from sheet 2, it's toward. So again, these directions are just coming from the idea of field lines go out from positive and into negative. Now, if we think about this equation, or how I derive this equation, nowhere in this equation actually did distance, or R, away from the sheet come into play. So when we're finding R, if these things were uniformly charged, these things would totally cancel out here. They don't, because they're different. But essentially we would say on the left, the total electric field is equal to E2, which is to the right, minus E1, which is to the left. On the, what, yeah?
It says no cat. It says no cat.
Yeah, I hear that. Okay, in the middle, they're both pointing right, so I'm going to say it's plus. And then on the right side, the total is going to be equal to E1 minus E2. So again, to get these values, I'm just looking at what direction, like a three body almost, just looking at what direction the arrows are pointing in. Okay, so I just go find each of those electric fields and I add or subtract to get my answer. So the electric field from sheet 1 is equal to the density 6.8 microcoulombs, so times 10 to the negative 6 coulombs per meter squared, divided by 2 times epsilon naught, 8.85 times 10 to the negative 12. And the electric field from sheet 2 is equal to 4.3 times 10 to the negative 6 coulombs per meter squared, divided by 2 epsilon naught. Easy peasy. And so I'm going to cheat. I didn't bring my calculator down. Let's see what we get for those two electric fields. From the positive one, this ends up being 3.84 times 10 to the 5th newtons per coulomb. And from the negative one, this ends up being 2.43 times 10 to the 5th newtons per coulomb. And then I can just go and add them, right? So here, E2 minus E1, E1 plus E2, E1 minus E2. And so that gives me, I don't see the answers. Oh, sorry. The middle one ends up being 6.3 times 10 to the 5th newtons per coulomb. And then the left and the right, because we're basically just looking at the difference, right? They both end up being 1.4 times 10 to the 5th. Oh goodness, I'm running out for 1.4 times 10 to the 5th. The one on the left, because it's E2, which is the smaller number minus the larger one, ends up being negative overall. And the one on the right, because it's the larger number minus the smaller, ends up being positive. And so that's it. So again, sheets of charge, you have a couple problems with it. If it were a single sheet, all you do is use this equation. It's very, very simple. But if you have, and we only take it as far as going 2 sheets. So if it's 2 sheets, you set it up like this. I would always go and draw my field lines so that you have a good idea of whether you need to add or subtract. And then you plug and chug and add or subtract. And that's it.